Before we get to discussing the one of the world's best enzymes, let's just do an overview of the de novo nucleotide biosynthetic pathways. So there are two pathways, one for the synthesis of purine nucleotides such as ATP and GTP, and another for the synthesis of pyrimidine nucleotides such as UTP and CTP. And those two pathways use different strategies. The purine pathway then starts out with this activated form of ribose. We use simple metabolites then to build the purine ring right onto the ribose to produce then the first purine nucleotide synthesized in the de novo pathways, which is inosine monophosphate, or IMP. And then IMP is converted into ATP and GTP. The pyrimidine biosynthetic pathway uses a different strategy. In that case, we build the pyrimidine ring first, and then we combine it with PRPP to form the first pyrimidine nucleotide, aridine monophosphate, OMP, which is converted into UTP, and then the UTP is converted into CTP. So then, in this way, we make all four of the nucleotides that we need for transcription. Okay, so let's look at this pathway in a little bit more detail, the pathway from simple metabolites to UMP. And so here is that pathway. We start out, as I said, with simple metabolites like glutamate, aspartate, and bicarbonate, and we assemble them together to form a pyrimidine derivative, namely orotate. Okay, orotate looks just like uracil, except it has this extra carboxylate group here. And then that orotate now reacts with this activated form of ribose to form aridine 5' monophosphate, OMP. And OMP then is the same as uridine monophosphate, except once again, we have this extra carboxylate group attached to the C6 carbon of the pyrimidine ring. Okay, then what we need to do to form UMP is to remove that carboxylate group. And so that's the job of this enzyme, OMP decarboxylase. It releases this carboxylate group as carbon dioxide to produce UMP. Okay, and so it turns out that this enzyme, OMP decarboxylase, that catalyzes this decarboxylation reaction can be thought of as one of the world's best enzymes. And so what do we mean when we say it's one of the world's best enzymes? Well, there are lots of ways to judge enzyme quality. For example, you can measure rate enhancement, and we already know what rate enhancement is. We've talked about it earlier in this quarter. Rate enhancement is simply the kcat for an enzyme divided by the knon. Okay, the kcat, or the turnover number for the enzyme, divided by the first order reaction rate for the uncatalyzed reaction, knon. That's not the only way you can measure enzyme quality, though. There are other ways. You can measure catalytic efficiency, which is something I think you learned about in 153A, but we'll go over it again in just a minute. And you can also measure something called catalytic proficiency, which in all likelihood is a new concept to you. So we'll be learning about catalytic proficiency as well. Okay, so let's review what catalytic efficiency is. So here is the familiar Michaelis-Menten equation. The velocity, or the initial velocity of an enzyme catalyzed reaction, is equal to kcat times the total enzyme concentration times the substrate concentration divided by the Michaelis constant Km plus S. Okay, and the Michaelis constant Km is really just the concentration of substrate that gives you half maximal reaction velocity. Okay, so let's suppose that we are under conditions where the substrate concentration is much less than the Km. In other words, we're down here somewhere in this saturation curve. And so under those conditions, then, very little of the enzyme will actually be bound to substrate. most of it will be free. And so under those conditions, we can approximate the total enzyme concentration as the free enzyme concentration. So we can replace E sub T with just E. The other simplification we can make under these conditions here then is we can ignore the substrate concentration in the denominator because it's so much smaller than the Km. Okay, and therefore now this rate equation simplifies to the velocity of the reaction is equal to Kcat divided by Km times the enzyme concentration times the substrate concentration. Okay, and so this really now is in the form of a second order rate law. It tells us the rate at which the enzyme and the substrate react to produce products. Okay, and so this is a second order rate law, as I said, in which the two reactants can be thought of as the enzyme and the substrate, and then Kcat over Km is simply the second order rate constant, or it's a pseudo second order rate constant that governs the rate of this reaction. So Kcat over Km, as it says here then, is the second order rate constant for the reaction of the enzyme with the substrate at low substrate concentration. It's also, you can also think of it as a measure of the efficiency with which collisions between the enzyme and the substrate lead to the formation of product. And so it's sometimes termed the catalytic efficiency. Okay, if every time the enzyme collides with the substrate, we get a productive reaction, we would say that that enzyme has achieved catalytic perfection. Okay, another way of expressing that is to say that that enzyme is diffusion limited. And that's because every time, as I said, the enzyme and the substrate collide, a reaction occurs. And so if an enzyme has achieved catalytic perfection, if it is diffusion limited, it turns out that Kcat over Km will be in the range of 10 to the 8th to 10 to the 9th molar to the -1 seconds to the -1. Okay, so that's catalytic efficiency. What about catalytic proficiency? Well, catalytic proficiency is really just the catalytic efficiency divided by the rate constant that governs the uncatalyzed or the non-catalyzed reaction. So it's catalytic efficiency divided by K-non. And since, as we just saw, catalytic efficiency is equal to Kcat over Km, catalytic proficiency is equal to Kcat over Km, all divided by K-non. It's a better measure of enzyme quality than the rate enhancement, which, as I mentioned, is just Kcat over K-non, because unlike rate enhancement, which doesn't include Km, catalytic proficiency includes Km, so it takes the Km into account. It also has an advantage over catalytic efficiency since it has no theoretical upper limit. As we just learned, the catalytic efficiency has a theoretical upper limit. No enzyme can do better than the diffusion limited rate. Okay, and so catalytically perfect enzymes all have roughly the same catalytic efficiency, somewhere into the 10 to the 8th to 10 to the 9th molar to the -1 seconds to the -1 range. Let's look at the units of the catalytic proficiency. So what are the units of Kcat, Km, and K-non? Well, the units of Kcat are just inverse time, so seconds to the -1, just like any first order rate constant. Km can be thought of as a concentration. It's the concentration of substrate that gives you half maximal reaction velocity, so it has units of molar. K-non is usually a first order rate constant, so it also has units of seconds to the -1. So if we analyze then the units of catalytic proficiency, we see that it has units of seconds to the -1 divided by molar, all divided by seconds to the -1. And if you simplify this, it comes out to molar to the -1. Where else do we find a constant with this kind of units? Well, as it says here, equilibrium binding constants also have units of molar to the -1. Okay, and so here is a binding reaction. A plus B bind together to form the AB complex. The equilibrium constant for this reaction is sometimes called an equilibrium binding constant because it's the equilibrium constant for a binding reaction. Okay, and so the equilibrium constant for this reaction is just the concentration of the product divided by the concentrations of the products of the two reactants. Okay, so it's concentration of AB divided by the concentration of A times the concentration of B. And since these are both molar concentrations, then all three of these, I should say, are molar concentrations, then the units of an equilibrium binding constant are once again molar to the -1. Okay, so the catalytic proficiency is some kind of a binding constant, it would seem. What kind of a binding constant is it? It turns out that the catalytic proficiency is the binding constant for this reaction here. It basically tells us the binding affinity of the enzyme for its transition state. Okay, and that's really interesting because that's something that you could never measure directly, right? You can't measure the binding constant of a transition state for its enzyme directly because the transition state is by definition unstable. It's in transition, right? So you can't isolate the transition state and measure its affinity for the enzyme directly. But in effect, you can do that by measuring the Kcat, the Km, and the Knon for any given enzyme. And by combining those in the way we saw on the previous slide to get the catalytic proficiency, you're actually also coming up with a measure of the affinity of the transition state for the enzyme. So why is that significant? Well, that's significant because what is it that enzymes do? Well, what enzymes do basically is to stabilize transition states by binding to them. Okay, and so the whole idea of chemical catalysis or the theory of transition state stabilization is that enzymes bind to the transition state and stabilize it relative to the ground state. Okay, so by telling us how tightly the enzyme binds the transition state, the catalytic proficiency is really kind of the ultimate measure of enzyme quality. Because really what enzymes have evolved to do is to bind to transition states. In theory, the more tightly they bind to a transition state, the better enzyme they will be.